people in the front row are supposed to always remind me. Now, I didn't know that. Okay. So, all right. So this local max, local min. So the next thing they talk about, increasing, decreasing. So this graph is decreasing until here, then it's increasing till here, then it starts decreasing again. Okay, the terminology we're going to use a lot. Next one they talk about is concave up and concave down. So right through this portion of the graph, this graph is concave up. So anytime the graph is curving, it's either concave up or it's concave down. This section is concave down, up. This section is concave down. Now it doesn't have anything to do with increasing and decreasing. See, this graph's decreasing, but it's concave up. Here it's increasing and it's concave up. Here it's increasing but concave down. Here it's decreasing and concave down. Okay, so concavity has to do with the curvature. Somewhere in there there'll be a point, maybe it's B, I don't know for sure on this one, but somewhere there'll be a point where it switches. It's moving along here, curving up, curving up, curving up, and then all of a sudden it switches and starts curving down. That's called an inflection point. The inflection point. So those are all terms that may come up on the quiz when we're looking at a graph, name the inflection point, where's the local max, that kind of stuff that might happen. All right. So you want, it's nice on the calculator we can trace to like those maximums. When you trace, it's not true of an inflection point, but when you trace, you know, you trace along, you get to a peak, it will stop and it'll say maximum. Here's the maximum. Find it for you automatically. The same thing with zeros or roots, x-intercepts. When you trace, it'll say 0 right when you hit an x-intercept. So it'll find those for you automatically. Okay, next page. If you look over on page 15, that just shows some table function values plotted. Not a big deal. Turn to the next page. Oh, okay. I wanted to skip over this. This picture is actually back on page 14. One of the things you'll probably have to do on the quiz is I give you a graph with some description of what it represents. Now this one is like an illness. So S stands for susceptible, I stands for infected, R stands for recovered. Okay? Well, in the beginning, most people are susceptible, hardly anybody has the illness. But as time goes on, the I graph starts going up because more and more people are getting infected, so then they're not considered susceptible anymore once they've got it. And then eventually they start recovering, so the recovering graph goes up. So if I ask you questions on day 15, how many are infected, or you know, that kind of thing. On what day did the susceptible get below 10,000, or you know, whatever. Just be able to read and understand and explain what's going on with graphs and functions. Okay, that's going to be a big part of what we do. All right, now we can move ahead to page 16. Actually, I'm going to skip this and come back to it. So now I want you to go to 18, page 18. And we're going to talk about, and any of this you want to write down is fine. We're going to talk about even, odd functions, and we're going to talk about periodic functions. So, okay, so even functions. Somebody remember something, anything about even functions? There is a component of symmetry, yes, to even functions. More specifically, which axis? One of the axes, yes.
Across the x-axis.
Well, let's talk about symmetry across the x-axis.
Nope.
Would that be symmetry across the x-axis right there?
Yeah.
That would be symmetry across the x-axis. What kind of function is that?
It's not one.
It's not one, right? So no function would have symmetry across the x-axis. So it must be the y-axis, right? Give me a function that has symmetry across the y-axis.
Absolute value.
Yeah, good one. The old parabola, y equals x squared. This is the first one they said in the other class because somebody had a notion of remembering something about even functions. Even meaning the power is even. And that is true in a limited way. Okay? So let's, on your calculators, I'm going to grab somebody to be the presenter here. Go to your screen here, anonymous person. Logan, thank you. Go to your graph screen and put in y equals x. Yeah, let's get rid of that one. So go hit the tab. We'll bring that up real quick. And let's delete that out of there. And here's what somebody said in the other class. They said y equals x squared. And then somebody said if the highest power was even, then it was going to be an even function. Oops. You got rid of the whole F1. That's okay. Type F1 parenthesis x equals, okay? And then put in x squared. And then somebody asked me this too the other day, so I thought I'd share with everybody. Hit window or menu. Menu window is number 4. And then if you hit 5, zoom standard, that takes you back to just a normal kind of graph. Oh my gosh, what happened? Arrow back up there, Logan. What? I know you put it in there. Arrow up again. Oh, okay, all right, arrow down. Okay, just delete it the old-fashioned way. There you go. I don't know what happened there. Probably, I don't know. Put in x squared. All right, hit enter. All right, so clearly that has axis with symmetry with the y-axis. Okay, now change it. Go up and change it to x squared plus x. And so I asked the other class, is this going to be an even function? And some of them said yes, and then some said no, it's an odd function. Because if you add the 2 and the 1, you get 3. Which one is it? Or here's the choices. Is it an even function? We haven't talked about odd yet. Odd function or neither. It's actually a neither. Most functions, quite honestly, are not even or odd. Most of them are not either one. Okay? So just because it has an even power does not mean it's an even function. So to be an even function, it has to have y-axis symmetry. Okay? It has to have y-axis symmetry, which, of course, y equals x squared does. So it's a good way to remember. If you can just remember x squared because it has an even power and the symmetry it has, it's an easy way to remember what even functions do. Now another way to do this, and Mrs. Payne I know made you probably work this out a little bit to prove something was an even function. I'm not going to get into that, but you're going to have to at least explain that it's got this symmetry, is this right here, which basically means if you put opposites in, you'll get the same thing out. That's what that is saying. You put in x and negative x, you'll get equal outputs. F is the output. So if I put a 2 in here and square it, I get 4. If I put a negative 2 in and square it, I also get 4. So opposite ends, same thing out. That's what y-axis symmetry means. What's the trig function that has y-axis symmetry? Picture those trig graphs. Which one? Cosine. Yes. Think of the cosine graph. Goes like that, goes like that. It has y-axis symmetry. You do pi halves, cosine of pi halves. Oh, that's a bad one. Cosine of pi is -1. Cosine of negative pi, also -1. Right? You get the same output when you put in opposites. Those are even functions. Okay, what are odd functions? Give me some examples of odd functions. Give me some examples of odd functions. Y equals x cubed, right? Y equals x cubed. It looks like this, kind of comes up, does this. That's what we're going to talk more about these tomorrow. Okay, what kind of symmetry is that? It's not x-axis. It's called origin symmetry. Origin symmetry is the name of that for odd functions. The way you write the notation of that, oops, is this here. When you put opposites in, you get opposites out. Opposites in, you get opposites out. If you do 2 cubed, you get 8. You do -2 cubed, you get -8. So opposites in, 2 and -2, you get out opposite y values, 8 and negative 8. Opposites in, opposite out, but most functions don't operate that way. So most functions aren't either one. What's the trig function that has origin symmetry? Sine has origin symmetry. Sine is an odd function. Goes up and down here and down through there. Has origin symmetry. If you put pi halves in, you get 1. You put negative pi halves in, you get negative 1. Opposites in, opposites out. Okay? So it will help us in calculus if we know a function's odd or if it's even. There'll be some advantages to knowing that information. Okay? All right. Last one I want to talk about, and then we're going to get into the part there we skipped, is periodic functions. Periodic functions. Okay? Periodic functions. These are two examples of periodic functions. If you just had to describe to somebody, little brother or sister, about what it is that makes a function a periodic function, what would you say? What one word would come to mind? Periodic function. What one word would come to mind?
Period.
Period, okay, but then that's kind of in the name, so that wouldn't be that helpful, would it? What else?
Origin, y-intercept.
Yeah, I'm talking about your
Here.
5th grade brother or sister who doesn't know what an x-intercept is. Repeats, wouldn't it? I mean, wouldn't that be? I think you were making it too hard. To me, I don't know, maybe I'm too simple. To me, when I think periodic, I think repeats. Now, the danger in saying that something repeats is sometimes we think of things that really don't repeat. Like, for example, if I had a graph like this. Does that repeat? Well, some people might think of it as repeating, right? It kind of has this pattern, I guess you might say. Is that periodic?
No.
No. What has to repeat? The y values have to repeat. Like, for example, this y value repeats at specific x intervals, right? This y value right here repeats. Now, you got to be careful. You say, oh, it repeats right there. Well, not really, because then there'd have to be one there, and there'd have to be one there, right? So what you would say is you'd say this y value repeats there, and then there, and then there. So this distance from here to here is the same as that distance from there to there. Every point on that graph has a repeating y value at in that same width interval. And that's called the period. Now, of course, we know sine, cosine have a period of 2 pi. Those are the most famous ones when we deal with periodic functions. But here's one down here. That's not a sine or a cosine, but that is also repeating. Here's what I'm going to want you to be able to do with periodic. So you already learned about sine and cosine, did all that. What I'm going to want you to be able to do is handle it with function notation. So let me give you this information. Let me tell you that f of x is periodic. Period is 4. And I'm going to tell you that f of 3 is -1. And I'm going to tell you that f of 10 is 17. So that's all I'm going to tell you. No equation, no graph, no nothing. Okay? And then I'm going to ask you, what is f of 7? What is f of -5? And what is f of 22? And I would also ask you, true or, not true of, true or false Okay, first of all, what is f of 7? Anybody? Negative 1. Why? We only got a couple of options, right, Teresa? Why? Idea? Jazzy?
Because the period is 4.
Right?
And so -1 would repeat itself. So like if it starts at 3 and then at 7 again, that's 4 away.
Again, I want you to really understand function notation. Understand the number in here is the x, the number out here is the y. So if I'm here at 3, -1, that's exactly what I've told you, is that's a point on that graph. So we're at 3. If the period is 4, when I go over 4 more units, I'm going to get that same y value out, right? Well, 4 more units from 3 is 7, right? So f of 7, that's 1, so that's 1 period away. It's got to give you the same y value. What about f of -5? -1. Why? Because it's 8 units back to the left from 3, right? So if you're at 3, you go 8 units back here to -5, you're going to, that's 2 periods away. So you've got to get -1 again. What's f of 22? 17. Because it's 12 away from 10. So f of 10 way out here is 17. So you go 12 units, that's 3 periods away. You're going to get 17 again. We don't know what's going on in between, but we know those values. Okay? Is this true? What does this mean? This leads into the next thing we're going to talk about. What's f of x plus 8 mean? Hint, it's a shift in the graph. It shifts to the left 8. So if you take this output and shift it to the left 8, do you get the same output? Mm-hmm. Yes, because that's 2 periods. So whatever this output is, we don't know what it is, but it's shifted 8 to the left from this output. We know they have to be equal, because periodic function repeats those values. So see, there's a lot of different ways to talk about periodic, but also understanding function notation, right? And I want you to be able to do that. So these are some of the questions you're going to be asked probably in the homework and also maybe on the quiz about periodic. Okay? All right. So last thing I want to do, if you turn back, it's not a big deal if you follow in the book, but the last thing is transformations of functions. A lot along the lines of what we just talked about with shifting left. We want to be able to take any function and be able to describe and graph and look at its transformation. Now there's different types of transformations. A translation is a left-right shift or an up-down shift where you just slide the whole graph. That's a translation. A reflection is when you flip it. So you can flip it around the y-axis, which would be a horizontal flip, or you could flip it around the x-axis, which would be a vertical flip. Right? That's a reflection. And a dilation is a stretch or a shrink or a compression. Okay? So we can either horizontally stretch or shrink, and we can vertically stretch or shrink. Those are the things we can do to function. So here's what I wanted. I just want to run through this with you real quick. Let's see if we can get to 100. All right. So what does a transformation, they're going to be pretty easy and they'll get a little trickier, but this will run through all the possibilities and then we'll show you how this is going to look on your homework. What does f of x transformed to f of x plus 8 do to the graph? 8 what? Up. Now let me give you my simple way of remembering this, what I think is simple. If the action is outside of the function, then it affects the output. It's vertical. If it's on the outside, it affects it vertically. If it's on the inside, in the parentheses, inside the function, it affects it horizontally. It's in with the input. So that's the x value. It affects it horizontally. If you remember those two things, I think it's helpful. The other thing I usually remember is when it's on the inside, when it's a number on the inside, it affects it the opposite of what you might think it does. Like the plus 8. You might think plus 8 is going to go right. It actually goes left. Okay? All right, so what did we say this was? Up 8. Plus, we would think it's on the outside, and actually we would think it would. It goes up 8. Okay, here we go. 10. All right, we're rolling. What's this one? Right 3. Brilliant. What's this one?
Left 2.
2 left.
Right 4.
Right 4,
Down
down 1. Right and down. Right and down. Left.
6 out.
So I might just ask a question that easy. It'd give you something like that, and all you have to do is write out, it'll shift the graph left 1 and up 6, right? Might be that easy. So left 1 and up 6, right? Okay, then what?
Right 5.
Right 5, 2 up. Okay, now what?
It stretches it
It's
horizontally.
inside, so that's horizontal.
It stretches it.
No, it shrinks it, because when it's on the inside, it acts the opposite of what you would think it would do. So what happens is that will shrink it by a factor of 4. Now let's make sure we understand what that means. What that means is, now it's going to, which way do we say horizontally? So if you have a value out here when x is 4, the new value will be where?
That's 1.
At 1. It shrinks by a factor of 4, meaning divide. So if you have an x value at 4, it'll be in at 1. A negative 4 will be in at negative 1. If you have a value of 2, it'll be in at 1/2, because it'll go in 2 divided by 4 is 1/2. Negative 2 will be in at negative 1/2. Everything comes in towards the y-axis. So it's a shrink, meaning, but it's by a multiple factor, right? So it's everything divided, all the x values divided by 4 is how it shrinks in. And you'll see that when you have to do it. So anyway, all we had to say here is shrink horizontal. Okay, what about that? To reflect, anytime you have a negative, it's a reflect. It's horizontal, right? It's on the inside, so it's horizontal. So you reflect horizontals around what?
The y-axis.
The y-axis, okay? It's a horizontal reflection, but so that means around the y-axis. Okay, a 2 on the outside. So outside means it's got to be vertical. It's a stretch. On the outside, it acts the way you think. So 2, 3, 4, big numbers, bigger than 1, are actually going to stretch. Okay, if it's on the inside and it's a 2 or a 3 or a 4, we saw it was a shrink. So it's a vertical stretch. Okay, 5 on the outside. Vertical stretch. So what that means then, again, a vertical stretch means if you had y value of 1, it's now a 5. You had y value negative 1, it's now a negative 5. So it's going both directions. That's a stretch. Okay? All right, what's this? 1 right,
Down.
6 down. Okay, we're 75.
7 up.
7 up.
Right direction.
Down 3. Why are they getting so easy all of a sudden? Aha. Vertical shrink. 1/9. Now again, that'd be by a factor of 9. So a vertical shrink would be, with a 1/9 would be, you have 9, now that's at 1. Right? So it'd be by a factor of 9, or multiply by 1/9, I guess you might say. Okay, so that's a shrink vertically. Down 7, throwing these easy ones here. Reflect
Across the x-axis.
x-axis, because it's on the outside, so anything on the outside is vertical, right? Outside is vertical, so it's going to be a reflect on the x-axis. Okay, vertical, it'll reflect about the x-axis. It's on the outside, so it's a stretch vertical. Stretch horizontal by a factor of 4. So that means if you have an x value of 1, it's now stretched out to 4. You have a negative 1, it's stretched the other way to negative 4. Okay, stretched horizontal. Oh, hey, we're in the challenge zone. All right. Oh, wow.
What does it mean by that?
Right 4, that, I don't know. You're above 90. Stretch, because when it's on the inside, it acts opposite, so that's a stretch horizontal. Shrink vertical. Up 1.
Right 2.
Right 2.
Left 9.
Now what it hasn't done is give us any
Putting it all together.
shrink vertical where you have several of them, right? Which, well, we've had a few translations, but not the other ones. Right 2, up 10.
Right.
I would have thought
Down 3.
up 3. All right. Woo. All right. So what will that look like on your homework? That's going to look like this. So you have, so there's a series of homework questions where they give you something like this. Now I've got some graph paper underneath the overhead over there if you want to use it on your homework, because you've got a series of about 5 or 6 problems where you're going to actually redraw this graph, but shrinking it, stretching it, shifting it, whatever. And when I come around and look, I want to see some decent graphs drawn. So for example, if this is g of x, and they said to do g of x plus 1, well, that's pretty easy. All of these points, I would look at these points, to be honest, if I'm working this problem and I've got to shrink or stretch a graph, I would probably pick out some of the important, the corners, the intercepts, those kind of things, and I would look at those. So these are all just going to shift up 1, right? So when you say the graph shifts up 1, if you actually want to draw it, you have to actually take some of the points and shift them up 1. And so there would be your drawing. Okay, so that's pretty easy. So shifts are pretty easy to do. The trickier ones are when you have a couple of things to do, or you have, like we said, that. What's a 2 in there do? Shrink horizontally by a factor of 2. So that means this value, which has a x of -5, is going to be right there. This point, which is at -4 down here, is in at -2. So everything's shrinking in horizontally. This point that's at -2 is now going to be at -1. This point at 0 is still at 0. This point that it's at 1 is going to be in at 1/2. This point that's at 2 will be in at 1. And this point that's out here at 5 will be in here at 2.5. And so I'll have this to there, and then up, and there you go. So that graph is now shrunk by a factor, or compressed by a factor of 2. Okay, so that's the kind of thing you'll have on the homework. All right, so you've got the last 20 minutes or so here, 25 minutes to work on. I think that's pretty much everything. So work on 1.2. There's quite a few of them. It's not quite as bad as it looks, I don't think. But so 1.2 on your assignment sheet. Don't forget about that scavenger hunt worksheet that's due on Monday. Okay. Answer books up here if you have any questions.
Over here.